Hello everyone, I am BUK working as an assistant professor of physics in Dr. BRR Government College at Chella. So in our last video we tried to understand and find the electric field intensity due to an infinite conducting sheet of non-conducting sheet of charge. So in today's video lesson we try to find the electric field intensity due to an infinite conducting sheet of charge, and also we try to understand the definition of electric potential, which is denoted by V. Okay, so anyway, we just move on to the topic now. So this is electric field intensity due to an infinite conducting sheet of charge. So in our last video we just determined E due to an infinite non-conducting sheet of charge. So there you studied what is a non-conducting sheet of charge and how do we determine the electric field intensity due to such a system by using Gauss theorem. So similarly, in this slide we try to understand what is a conducting sheet of charge, and that means what kind of distribution it comes under, and also the basic, that means diagrammatic part of the infinite conducting sheet of charge. How do we represent it, and how do we understand the basic construction of it? All those things we try to get in this slide. So anyway, what is an infinite conducting sheet of charge? So that you try to get. So this is a conducting sheet of charge. Okay, can you see this one? It's a conducting sheet of charge that I have assumed. Okay, so it's a sheet of charge, or in simple words you can say that if the charge is uniformly distributed on a conducting sheet, that system we call it as conducting sheet of charge. So that's it. It's a normal definition. If the charge is uniformly distributed on a conducting sheet, then that conducting sheet we call it as conducting sheet of charge. So that means on that conducting sheet the charge will be uniformly distributed. So that we call it as the conducting sheet of charge. So what is the meaning of infinite? From the name itself you can say that its dimensions are infinite. So that means its length and the breadth are infinite, but its thickness will be very smaller. Okay, infinitesimal, you can say that infinitesimal. Okay, anyway, for understanding the derivation part, I have drawn its thickness by a finite distance for our understanding. Okay, so anyway, so this is how the infinite conducting sheet of charge looks when we see it from the side. So this we call it as the side view of the infinite conducting sheet of charge. Okay, so now the same system of charge, which is the infinite conducting sheet of charge, when viewed from the front it looks like this. It looks like that means it looks like a line. Actually it's a line, but for convenience, for the derivation part, we have taken its thickness by a finite value. Okay, so that you just check it out. So that means it looks like a rectangle now. Rather, if you consider, if the thickness dimensions are drawn bigger, okay, represented by a finite length, finite value, it looks like a rectangle. So this sheet looks like a rectangle, and on this sheet, you know that since this sheet is made of conductor, whatever the charge that has been given to it will be uniformly distributed on its surface, and no charge will be present inside it. Okay, so that means whatever the charge that has been given to it, the charge will be present only on the outer surface, not inside it. so that you have to get it. So whatever the charge that was seen in this diagram, so that charge is uniformly distributed on its surface. Okay, so no charge is present inside it, so that you have to understand here. So no charge is present inside this sheet because it is made of conductor, and why it is so we already discussed many times in our previous topics. Okay, so that you try to get it. And the charge will not be present on this upper surface and lower surface. Why? Because its dimensions are infinite, right? Since its dimensions are infinite, the sheet is spreaded in upward and lower directions, but I am not drawing that parts. So and hence whatever the charge that is given to this sheet of charge is distributed on the right side and the left side of the sheet, that you can understand, not on upper and lower surfaces, because its dimensions are infinite. Is that clear? And I hope it is fine. So next one, since I have taken the charge that is present on this surface as positive, you know that for positive charge the electric lines of forces are always directed outwards. Is that clear? So now the electric lines of forces that are traveling from these positive charges can be represented with these arrows. So that means this system of charge, which we are taking it as an infinite conducting sheet of charge, it will be having some electric field around it, and that electric field can be represented with the help of electric lines of forces that are shown here. So the electric lines of forces are directed outwards because the charge that is present on the surface is positive. So in our earlier cases, the direction of electric field was in all the directions, but this is a different case. It's a sheet of charge, so please remember, since it's a sheet of charge, the electric field will be, that means the electric lines of forces that are arised here will be only either toward, sorry, not only, it will be in outward directions, that too towards left and towards right. So only in these two directions the electric field will be there, because the charge is uniformly distributed throughout its surface, right? Okay, so that means the electric line of force, if I take some marker here, so the electric line of force will be directed outwards like this, and the electric line of force will be directed outwards like this, and so on. So whatever the charge that was present, okay, so due to that charge the electric lines of forces will be directed outwards. Here in this case, since it is sheet of charge, it has some length and breadth, right? It has some length and breadth, and hence whatever this is the side view, and if you see this entire image from the front, what happens, all the electric lines of forces will be directed only towards right and left, not in all the directions. So the electric field will be directed only towards right and towards left. So whatever the electric field that is arised here towards right, this is the right side of the sheet, okay, this is the right side of the sheet. Whatever the electric field that is present or that is arised on right side of this sheet, that will be due to the charge that is present on the surface that is present on right side. So please check it out. So here whatever the electric field that we are getting, so that electric field is due to the charge that is present on this surface, okay. And similarly whatever the electric field that is arised on left side of the sheet, that will be due to the charge that is present on the left side. That you have to understand here. And inside this sheet, you know that E is always 0. Why? Because you know that inside the conductor the electric field intensity will be 0. So that you try to get it here. So anyway, and one more thing is that, as from the diagram itself you can easily see that whatever the charge that is given to this system is distributed uniformly on its area, right? Since the charge is distributed on its area, this system of charge will be an example for surface charge distribution, okay, surface charge distribution. So you know that there are different types of distributions of charges. One is linear charge distribution, another one is surface charge distribution, and the third one is volume charge distribution. So since the charge is distributed on the surface area of this sheet, it becomes a case of surface charge distribution. Since this is an example of surface charge distribution, whatever the derivations are, let me write this one, whatever the derivation of electric field intensity that we are determining here, that can be studied in terms of sigma. What is sigma? You know that this is surface charge density, which we define it as charge per unit area. Charge per unit area. So how do we determine it? So whatever the charge that is given to the system has to be divided by the entire area on which the charge is distributed. So that gives you the charge per unit area, which we call it as surface charge density. But unfortunately in this system, the dimensions of the sheet is taken as infinite, and hence the total charge that has been given to that entire sheet is unknown to us, and also the entire area of that sheet you cannot determine because its dimensions are infinite. But even then you can write the value of sigma in terms of charge that is present on a particular area element. So to find sigma, what you do is that you just choose any area element of that sheet. So this is the sheet, right? Conducting sheet of charge. You choose any area element that is present on that sheet of charge. So let us assume that this is the area element that I am choosing, in which the charge that is present is assumed to be Q. So if I take the marker to be present here, let us assume that the charge that is present within this area element, not this area. So these are all whatever the charge that is present here, that is coming out of this area element, right? I am not choosing this charges that are present outside this area that I am choosing. So this is the area that I am choosing, and if I assume that the charge that is present on this area is plus Q, and if I assume that its area is either A or ds, whatever the notation that you want, you can take it. So if I choose this area by capital A, and if I choose that the charge that is present in this area is plus Q, then by the definition of surface charge density, we can write sigma as the charge that is present in this area, that is Q, divided by the total area of that element that I have chosen, which is A. So from this equation I can write Q as sigma into A, and if I take that area element by ds instead of A, you can write it as ds. So that means in terms of surface charge density and Q, what is Q? Q is the charge that is present on the chosen element. Okay, you can write an equation which is given by this formula, that is Q is equal to either sigma into A or sigma into ds, so that you try to get it. Anyway, I am erasing it, and so that means the introduction part of this conducting sheet of charge is over. So the basic that means explanation of what is conducting sheet of charge. So what is its construction part, how the charge is distributed, and how the electric lines of forces are directed, and how we can write the surface charge density of this sheet of charge. All those things can be understood with the help of this slide. Okay, fine. So now coming to the derivation part. So now we can determine the electric field intensity of such an infinite conducting sheet of charge by using Gauss theorem. And as I already told you, since the sheet of charge is made of conductor, the electric field intensity inside the conductor will be 0. Is that clear? And further, that means to understand the concept of Gauss theorem, we are drawing the thickness of the sheet by a finite distance. Actually its thickness is very smaller, but I am drawing it bigger so that you can understand the concept easily. Okay, so that you try to get it. Actually, the sheet will be like this, right? The sheet looks like this. It looks like a line, but for convenience, for better understanding, what I am doing, I am drawing that thickness which is very very smaller in bigger dimensions. In bigger dimensions, that means I have drawn in such a way that the thickness is larger. Okay, but actually it is very very smaller, so please check it out. So I am erasing it. So fine. So this is the conducting sheet. So there is no charge that is present on this sheet right now. So it's a conducting sheet whose thickness is very very smaller, but drawn in bigger size to make it clear to you. That's it. So fine. Now let us assume that this is the charge that is uniformly distributed on its surface, and let us assume that the surface charge density of this conducting sheet of charge is sigma. Okay, you can find sigma, right, by choosing a small element. Anyway, we come to that part later. Anyway, to find the electric field intensity, we were following few steps from many topics, and the same topics, the same steps are followed here. So the first one is that you have to first choose the point P where you want to find the electric field intensity. So this is your system of charge. So to find the electric field intensity due to this system of charge, what you have to do? First of all, you have to choose the point P where you want to find the electric field intensity, right? So let us choose a point P. Anyway, you can choose the point P anywhere, not in this region, because here in this region the sheet will be present, and not in this region too, but either on left or right side of the sheet you can choose any point P which is present at a distance of small r. Okay, for convenience, let me choose the point P on the right side of the sheet, and so let us assume that this is the point P which is present at a distance of small r, where I want to find the electric field intensity. Okay, but you know that you don't know the magnitude of electric field intensity at this point P, but you know the direction of electric field intensity at this point P, right? So please remember. So here at point P, the electric field intensity will be directed outward. How the electric field direction will be, that we understood already in our previous slide. I hope you got it. Okay. So I have chosen point P, which is present at a distance of smaller from the sheet of charge, conducting sheet of charge. So next one. So next is that you have to construct a Gaussian surface here in such a way that it passes through point P. So that is the first condition. So that means you have to draw a Gaussian surface in such a way that it has to pass through point P. That is the first one. And second one is that it has to be symmetrical. Okay, it has to be symmetrical to make the calculation easier. So in this case, since it is the sheet of charge and the point P is here, the closed surface can be of any form. Okay, but it has to be symmetrical. That is the condition that we are speaking of. So if it has to be symmetrical, the Gaussian surface will not be a sphere at any cost, because it looks like this. And if the sphere is of this form, the environment that you see from the sheet of charge around it will not be same, will not be that means similar, and hence here the Gaussian surface will not be a sphere at any cost, and at the same time it will not be a cylinder also. It will not be a cylinder, but there is one important thing that you have to understand here. If the cylinder is vertical, the Gaussian surface will not be a symmetrical one, but if the cylinder is taken as a horizontal one, then the Gaussian surface is going to be a symmetrical one. This we already discussed in our last topic, which is in case of infinite non-conducting sheet of charge. So why it looks like a similar one, that also explained there. Anyway, here the Gaussian surface or the closed surface that is passing through point P and which is also symmetrical is going to be a cylinder. Okay, so and that cylinder looks like this, so please check it out. So this is the cylinder which is taken as horizontal. Okay, so now the height of the cylinder is 2r. What is the height? So from this point to this point, anyway, let me take the point here. So the height of the cylinder is from this point to this point, and the height of the cylinder must be 2r to make it symmetrical. I hope you understand the okay. So this I already discussed in our last topic. So this is the Gaussian cylinder which is passing through point P. Okay, and also symmetrical. So in order to make it symmetrical, the height of the cylinder has to be taken by 2r. If it is not 2r and something else, it will not be symmetrical, so that you try to get it. So now this is the point P which is present outside the conductor. So this is our conductor, conducting sheet of charge. This point P present outside the sheet, and the same point P will be present even inside the sheet also. Even inside the sheet also. Remember, in case of non-conducting sheet of charge, this point P was present outside the sheet, either on left side or on right side. The sheet was present, the point P was present always outside, but here this is different, that you have to understand. This is a conductor, right? So since it is a conductor, the electric field intensity will be 0 inside the conductor. That means the electric field is not continuous here. It's like broken. It is starting from the right surface and also starting from the left surface. The electric field is starting from right surface and left surface, but not in between. Okay, so that means it's like the electric field is broken out here, and hence what you have to do, you have to consider this region also. Inside region also you have to consider, and whatever the electric field that is present on right side, that will be due to the charge that is present on right side only. And similarly, whatever the electric field that you get on left side, that will be only due to the charge that is present on left phase. I already discussed all these things. Okay, I hope it is clear. So you have to understand the concept part first of all, the next derivation will be very easy. Okay, let me erase this one. So this is the Gaussian cylinder that I have drawn here, I have constructed here in such a way that it passes through point P and also symmetrical. Okay, so fine. And the next one, what will be our next point? So now you have to choose a small area element at point P, and that area element you can choose it as a ds. Okay, so this is the point P where I am finding electric field intensity. Now what you have to do, you have to choose a small area element here. So that means you can assume that the circular surface of the cylinder itself is very smaller, and the entire area of this cylinder you can take it as ds, which is a very small area, or else you can take it as capital A also. It's not a big deal. You can choose a small area element ds at point P itself, or else you can assume that the entire circular, this is circular surface, right? This is the circular surface of the cylinder. You can assume that the entire circular surface is having a very small area, and that you can take it as ds. Okay, so that you try to get it. So this is what I have constructed. Okay, so I have taken the area of this circular face of that cylinder by ds. Okay, then next, what is our next step? You have to draw the directions of electric field intensity and ds, right? So this is the cylinder that that is having, right? So whatever the cylinder that you have, it will be like this, right? It is your cylinder now. So you know that the electric lines of forces at point P are directed outwards. So this is the point P where I am finding. So you know that we already know, since the positive charge is present here. So this will be the direction of electric field intensity, and this is the circular phase, right? And this circular surface also will be like this, and whatever the ds that I have constructed here, and its direction will be perpendicular to it. That means even the direction of ds also will be like this. Okay, so this we already discussed. Anyway, but for convenience I am for clarity we are discussing all the points here. So let me erase here now. So now the directions of electric field intensity and ds we can draw here. If you draw, you can see here. So this is direction of E, which is directed outwards in right side, and the direction of ds is also out in outward direction, that too in the direction of E, and hence the direction of the angle between E and ds here I can write it as 0. Okay, so the next one is that you have to write the mathematical equation of the flux that is passing through ds, and that will be denoted by d phi, which I can write it as the dot product of E and ds. So now you know what is E and what is ds, and you also know that the angle between these two is 0 here, right? So this is the flux that is passing through ds element, and which I can write mathematically by the dot product of electric field intensity and the area vector at point P. So now to find the total, that means to find the electric field intensity, here we have to apply Gauss theorem, and to apply the Gauss theorem you have to find the total electric flux. Okay, so now you know that the flux that is passing through ds is denoted by d phi, which is equal to E dot ds. So now to find the total electric flux, what you do, you just integrate this equation. If you integrate this equation, I can write it as phi is equal to integral d phi, which I can write it as from equation integral E dot ds, and this integral E dot ds is the total electric flux that is coming out of this cylinder, right? So to find the total electric flux that is coming out of this cylinder, what we are doing here is that we are dividing the entire flux into 3 parts. Okay, so if you observe this diagram, we already discussed it. This cylinder will be having 3 phases, 3 surfaces, right? One is the circular surface which is present on the right side, which I have taken it as S1, and another one is the circular surface on the other side of the cylinder, which I am taking it as S3, and this is the curved surface. This is the curved surface of the cylinder. That means the surface S1 will be like this, and S3 will be like this, and the curved surface will be like this, right? So this S2 is nothing but the curved surface of the cylinder that I am considering. So now the total flux that is coming out of this closed surface can be written as the sum of the fluxes that are coming out of S1, S2 and S3, which are denoted mathematically here. So this is integral E dot ds with the limit S1, that means this is the flux that is coming out of surface S1, this is the flux coming out of surface S2, and this is the flux coming out of surface S3. So that you try to understand. Anyway, what are S1, S2 and S3, that you can understand from this diagram. And you know that dot product of A and B is AB cos theta, right? So like that you can write the formulas of E dot ds by expanding them. If I do so, I can write the total electric flux as integral S1 EDS cos theta, this is integral S2 EDS cos theta, and this is integral EDS cos theta with respect to surface 3, where theta is the angle between electric field intensity and the surface element respectively, and that means with respect to those surfaces. So now this is the first point. These points you need to understand here. So this is EDS cos theta with respect to S1, right? So that means now come to S1. This is surface S1. So at S1, the directions of E and ds are in the same y, and hence theta will be 0 here. The angle between E and ds will be 0, right? And hence in place of theta we have written 0 here. Similarly, take S2. This is curved surface, right? If I choose any surface element here, so this will be directed in upward direction, and at this point the electric field intensity will be towards right. So that means the angle between these two will be 90 degrees. Okay, and hence with respect to S2, the angle between E and ds is 90 degrees, which is denoted here. Similarly, in case of S3, in our last topic, at this point the electric field intensity was directed outwards, right? Because there was some positive charge here also in case of non-conducting sheet of charge, but here there is no such positive charge inside the conductor, and hence here there will not be electric field, there will not be any electric field here. So that means I can take the electric field intensity at this point P as 0, because this point P is lying inside the conductor, right? You also know that the electric field intensity at a point inside the conductor is 0. Okay, so that is known to you. Anyway, for convenience, if you assume that there is some electric field at this point, if you assume that, okay, and at this point the ds also will be in outward direction, and hence you can say that if it is there, because in case of non-conducting sheet at this point the electric field intensity was there, right? So if you assume that if there is electric field intensity, if it is inside the conductor, that theta will be 0, but actually this is not there, it is not there. If you assume that it is there, this is non-zero, but since it is not there, you can substitute 0 in place of e, that's it. Anyway, now coming to this one, so this equation I can write it as, since cos 0 is 1, okay, I can write it as it is e times ds, and here you know that cos 90 is 0, and hence that 0 is substituted here, and you know that here in this case cos 0 is 1, but unfortunately this is the point P which lies inside the conductor, and hence you know that inside the conductor electric field intensity is 0. So now from these three terms, this gets cancelled because it becomes 0, it gets vanished, it also gets vanished because it also becomes 0. The only term that is left here is integral e ds. So you know that e is constant, take it out, and integral ds is nothing but ds, you already know, we already discussed it. The total area of this circular surface is taken by ds, right, and hence you get e ds only. So this is the total electric flux that is coming out of this cylinder, Gaussian cylinder, in case of infinite conducting sheet of charge. I hope you got it. So now we know the formula for total electric flux in this case. Now the total electric flux is nothing but 1 by epsilon 0 times the charge enclosed by it. So this is Gauss theorem, you know this. You can write this equation as equation number 3. So remember, this Q is the charge that is present inside this cylinder, inside this closed surface. Okay, so on this conducting sheet of charge, the area that is that means you can say that the charge that is, if you assume that the charge that is present inside this closed cylinder is plus Q, if you assume it so, I can write the Gauss theorem by integral E dot ds is equal to Q by epsilon 0. Anyway, next one, from equation 2 and 3, if I compare these two equations, what I get? I get E ds is equal to Q by epsilon 0, and send this ds to right hand side, it becomes E is equal to Q times epsilon 0 ds. But you know that I can write Q in terms of sigma. So in this case I write Q in terms of sigma as Q is equal to sigma ds. Why it is so? Why and how I can write Q as sigma into ds? Remember, we already discussed in our in our first slide of today's video lesson. That is, this is the ds, that which is the area element that I have chosen on that conducting sheet. To make it clear, I am erasing everything. So can you see, can you observe this diagram carefully? This is front view, right? This is the front view. And if the same diagram is seen from side view, how it looks like? You cannot see a cylinder, rather you see a circle here. What will be this circle? This is the bottom surface of the cylinder that you are seeing here. You can only see circle now. So even on this sheet of charge, the that means the positive will be present outside this circle. Is that clear? And the area of this circle is how much? ds. And if the charge that is present in this circle, if I take it as Q, then I can write Q as sigma into, what is its area? Its circle area is ds, right? You already know that. So that means I can write Q as sigma into ds. So that you have to understand here in this case. So that means Q, I can write it as sigma into ds, and in the denominator we have epsilon 0 ds, and this ds gets cancelled, so you get finally sigma by epsilon 0. So this is the electric field intensity due to an infinite conducting sheet of charge which is coming out to be sigma by epsilon 0. Remember, sometimes in your examination they may ask you to find the electric field intensity at a point P just outside the conductor. So even that topic, that means even to that topic the answer is this one. Okay, even if they ask to find the electric field intensity at a point P just outside the conductor, you can write this answer. So this answer is applicable to two kind of questions. So one, they may ask to derive an expression for E due to an infinite conducting sheet of charge, that is the first one, and in another way they may ask you to find the electric field intensity at a point just outside the conductor. So just outside the conductor means this point P becomes just outside the conductor. So we are saying it just outside the conductor because the half of the cylinder is lying outside and half of the cylinder is lying inside the conductor, right? But its thickness will be very smaller in general. Though it is smaller, okay, though it is smaller, half of the cylinder is lying inside the conductor. It means that this cylinder height is very smaller. If the height of the cylinder is very smaller, it means that R will be very smaller. If R is smaller means what? Point P is lying just outside the conductor. Okay, so if they ask you to find E at a point at a point just outside the conductor, even to that question the answer will be the same one that we have written on this slide, so that you try to get it. So anyway, so that's it. We just move on to our next one. So this is electric potential. We just try to understand what is electric potential, the definition, and we will stop today. Anyway, what is electric potential, that we try to understand. Anyway, so you know that, let us assume that it's a positive charge, say some Q1, and you know that it will have electric field around it, right? And at different points, sorry, so this is plus Q, and you know that it will be having electric field around it like this, and at different points it will be having different electric field intensities, you know that. So for example, let us choose this point R. At this point this charge will have some electric field intensity, you know that. So let us choose that this is the point P where I want to find the electric potential. So to find the electric potential, let us choose one more charge, say some Q0. You can take this as Q2 also, Q1 also, because the point charge that we have taken here is plus Q. So other than Q, you can take any notation. So let us assume that some Q charge is present at infinite distance, and if you want to bring this Q0 charge to this point P, you have to do some work, right? And that work done in bringing this Q0 charge from infinity to this point is called as electric potential. So this is what you have to understand. Is that clear? So that means, what is electric potential? Electric potential is the work. So this is V. Electric potential is denoted by V, and it is defined as the work done in bringing Q0 charge. This is Q0, right, which is present at infinite distance. The work done in bringing a charge, Q0 charge, from infinity to this point is called as the electric potential at that point. And mathematically we can write that equation as V is equal to W by Q0. From formula itself you can write the definition. Work done in bringing a unit positive charge from infinity to that point, we call it as electric potential, and it is a scalar quantity, and it is denoted by V, and its units are volts, so that you try to understand. So this is electric potential. So we just try to understand the definition of it. In our next classes we try to derive the formula for electric potential of a different system of charges. Okay, so I hope it is clear. We'll stop here. Thank you once again.